So what we are going to do today is actually look at the kernel for feedback vertex set, okay, and use expansion lemma or whatever we did before. Okay, so just for okay, so we'll get to the expansion lemma as and when we require. Okay, so what is the plan for the kernel for the feedback vertexes? So the plan is first. So our plan is step 1 is to make the graph minimum degree 3 with some property. Make the graph minimum degree 3 with some simple preprocessing rule. Okay, so that's the step 1, which you might have seen it already, but we'll just, for the benefit of everybody else, we'll try to recollect it. Step 2, we'll see what happens if max degree, not min degree, max degree of the graph gets upper bounded. And step 3, finally, okay, how do we bound the max degree? And this is the place where expansion lemma will come into play, and we will have to design new set of reduction rules. Okay, here expansion lemma and new reduction rule. Yeah, very new reduction rule. Okay, quite a non-trivial reduction rule. Okay, so that's a plan. Now, how do we strip this? So you must have seen this in whenever you have been already designing the algorithm with log into the power k algorithm. So what are the rules for this? So some basic rules are, if there is a vertex of degree less than equal to 1, if there is a vertex v of degree at most 1, then delete v. So basically you have g comma k, you can show that because a vertex of degree at most 1 does not participate into any cycle, so they are completely useless object, and you can prove it that they are really completely useless object. Okay, rule 2. Okay, another thing, throughout this process it is possible that we might create multi edges, self loops and everything. So what we will be working with is multigraph. So we will be generally dealing with multigraph. Okay, so another rule is, which is called, I don't know what is it called, I don't know, forgot the name. Okay, basically what it is that if you have a vertex u v w such that degree of u is equal to 2, then short circuit u. What is it meaning of this? Is that you delete u and add an edge between v and w. Okay, so basically this operation, there could be already an edge between v and w, then you will get a parallel edge. Okay, that's where the parallel edge comes. Okay, so you apply these rules recursively. Like something is stuck in my name. So delete U and add an edge between V and W, and this can create parallel edges. Okay, but notice what else can happen. Suppose I have a cycle and you have been applying this reduction rule. If you do this, we do this, it can create self loop, right? So that is how you can get a self loop. So now we have a third rule. If I have a self loop, then this is a single vertex with a loop. It means every minimum feedback vertex set, this is a cycle with exactly one vertex. It must go in. So what is the rule 3? If there is a vertex V with self loop, then delete V and decrease the parameter by 1. So what is this? G comma K, and this is correct because any minimum feedback, any feedback vertex set of size at most K must contain V. So this is perfectly fine. Okay, so these are 3 basic simple rules. Now let's try to analyze what is the effect of when none of these reduction rules can be applied to the graph, right? Okay, so what can we say when reduction rules 1, 2 and 3 cannot be applied? Okay, then what can we say about it? Right, this all we can say at least, right? But we can also say something, right? Because after application of this rule, K decreases. It could be that the graph has a cycle, but my parameter is 0, right? We are saying a graph that has a cycle and we are asking, does it have a feedback vertex set of size 0? Well, answer is no, it cannot be, right? So for to take care of those, what is I call corner cases, you also have small rules like, okay, so you just add rule 4, if G is cyclic or G has a cycle and K is less than equal to 0, then say no, right? Then you actually have solved the instance. You have been able to decide in polynomial time whether whatever instance was given to you was a yes instance or a no instance. This is a no instance, okay? But now graph has minimum degree 3. That is what we have been able to achieve by applying this 3 or 4 simple reduction rule, because basically 3 simple reduction rule. This is a basically boundary rule, okay, just to say that, okay, let's halt. Now, so we are done with this, right? So we will always apply this rule. So we have been able to ensure with applying some simple pre-processing rule that the minimum degree of this graph is at least 3, okay? So let's just mark achieved, delta G is greater than or equal to 3. Now imagine yourself, I'm going to prove a small simple combinatorial lemma, okay, which tells us that if the graph has minimum degree and maximum degree both bounded in a graph of feedback vertex set, then feedback vertex set size is too large. Now think about it, why this should be true, okay? Imagine yourself, let's imagine the graph has minimum degree 3, okay? Graph has minimum degree 3. And suppose I also have an upper bound on degree. So suppose, for example, just to get a feeling for it, let's just ask ourselves that I have a graph G, and suppose minimum degree, maximum degree, both are equal to 3, for a just to get a picture, okay? Now, how many edges are there in this graph? So the number of edges in this graph is like 3n by 2, where if n is number of vertices. Now imagine yourself that after you have deleted a feedback vertex set, how many edges are left in the graph? After I delete the feedback vertex set from the graph, how many edges can at most be left in the graph? So suppose if I had a feedback vertex set of size k and I delete this, what is the at most? I'm just asking an upper bound. How many number of edges can there be in the remaining graph? N minus 1. No, if I deleted k, it has only n minus k vertices. N minus k minus 1. Why? Because it is a forest. Right? So as Diksha is saying, even if k is stupidly like 1, at best you can have n minus 1 edges. So at least logically, how many edges are incident to this modulator or this feedback vertex set? At least how many? N by 2. Because if there are n minus 1 edges here, then where are those? Like including this. Now if I delete one vertex, how many edges can I take care of? 3. Right? But I have to at least take care of n by 2 edges. So so the feedback vertex set size should roughly be n over 6 at least. Otherwise you cannot manage. Do you get it? Look at any feedback vertex set. How many edges are incident to it? At least n over 2. Because after I delete this, how many edges can this graph have? At most n minus 1, because it is a forest, right? But total number of edges in graph is how much? 3n by 2. So there are n by 2 edges which are incident to this. So now I have n by 2 edges which you need to take care of. So if I delete one vertex, how many edges can it delete? If the maximum degree is 3. 3. So how many times do I need to apply this operation so that this n by 2 edges are taken care of? So n by 2 divided by 3, so n by 6, right? So if I had a bound, not max degree, say delta, then I at least can fill n divided by 2 delta, right? Okay, more or less I gave you a proof, right? I mean, I can make a much further refined proof, but that's an idea, right? That's an idea. I mean, you can prove much more refined bound, but for all practical purposes, this is more than enough. Okay. So what is the lemma we proved? Okay, so let G be a graph with minimum degree 3 and maximum degree delta. Okay. Then G has then the size of a minimum feedback vertex set of G is at least okay. This is my first lemma which I had proved in my life. In 1 year. Okay. But now I don't even remember the proof. That's sad part of it. Okay. Okay. So let G be a graph with minimum degree 3 and maximum degree delta. Okay. Because I'll tell you what happens when you do science. Okay. The insight which I told you here, I didn't have. I was just playing around with boxes and this and try to get some inequality. But if you just think for a minute, like in a reality, I mean, for all practical purposes, I didn't need this bound. All I needed is this is good enough for all practical purposes. Like for every purposes, this is great. And this tells you more about feedback vertex set than this concrete bound. Why? This tells us that feedback vertex set is nothing but a vertex cover problem. A vertex cover problem which leaves a very sparse object here. And this insight can be exploited algorithmically in several occasions. Okay, fine. So let's try to prove this. Okay, so now here I have feedback vertex set, and here I have what I call G minus F, and let E of F denote the set of edges that are incident on F. What can we say about this? How many edges are here? At most, this many edges are there, right? Because n minus this minus 1. Now, let's try to bound the edge of F, a lower bound and an upper bound. So, what is one upper bound, a trivial upper bound on EF? Is delta times F, because every vertex has a maximum degree delta. But EF is at least how much? E of F is at least E of G minus this many number. Agreed? Right? Minus. Is this correct? Right? EF is all those edges which are not present here. So at least this many edges. Okay, very nice. But what is a lower bound on EG? 3NO by 2. Right? Right? Because the graph has minimum degree 3. So number of edges, this number is correct. Is it correct? Yeah, because this is a lower bound, right? It could be much more edges, right? And now let's subtract minus n, minus plus mod f, and minus plus 1. Agreed? This number, this is at least greater than equal to, what is this? N over 2, say plus f, forget plus 1, because this is okay, right? I am only saying at least. So now I can take f this side, right? Or rather than writing 3 here, I could have written here delta, because minimum degree of the graph is delta. So what will this will be then? So what should I write here? Delta minus 2, is it correct? Correct. And now is the bound doesn't follow? Should follow, right? If I move f this side, then it, yeah, so if I take f this side, so it is delta minus 1, so f is at least delta minus 2 divided by 2 times delta minus 1 into n, and that's how you get the bound, right? You just take this to inequality and then you will get the, right? But I told you why it happens. I mean, it happens because of this reason, right? The poor feedback vertex set has to capture many edges, and then if I have a budget of every guy can only capture delta guy, then I need n by 2 delta, right? And that is what basically we are getting here, right? So it's like a accounting business, okay? But this is a useful thing to have, okay? So now what we know, if a graph has blah, then blah happens. Okay, so now if I am able to bound the maximum degree of the graph, are we done? So what do we get a kernel for? What did we get? So now let me prove to you. I am going to rub this simple reduction rule because let's assume that we know it. So what we can prove are some very interesting, let's get to the core of the heart of the as quickly as we can go. Fine. Okay. So lemma. Let G be the class of graph such that maximum degree of every graph G in G is at most delta. Then feedback vertex set admits a kernel of size k delta, order k delta on J. I am going to prove this. So for example, G could be a graph class where every vertex has degree bounded by 100, right? Delta could be anything. Let us prove this because this will be the important ingredient. So what we know, we can apply all pre-processing rule and we can assume that the graph has minimum degree 3. So what does that mean? So delta is always 3, right? So first thing I check is that, so input is what? G comma k, okay, okay. Imagine yourself that all reduction, none of the reduction rule increases the max degree of a graph, right? If you delete, it can only decrease, right? And when you add a self loop, like you come, like when you remember, other rule was that you deleted someone and added an edge, but it was anyway counted as a part of this, right? So apply all reduction rules, okay, and obtain G prime K prime such that G has a feedback vertex set of size K if and only if G prime has a FVS of size K prime. Agreed? And the important point is delta of G equal to delta of G prime is less than equal to delta of G. It does not increase, and that is all that I care. Okay. And what is this? Minimum degree is 3. Okay. So now I check, okay, I check is K prime, and always notice that K prime was decreasing. So K prime is at most less than equal to K actually, right? Because every time, every application only decreases the value of K, it never increases. There are kernelization algorithm where K, it is good to increase K by +1 +2 because it helps us in dealing, but in general it does not, okay. Okay, so delta, so now what can I say about it? I say, hey look, if K prime is strictly less than say n times delta minus 2 is how much? Delta is 3, 3 minus 2 is 1, so forget it, divided by 2 times delta minus 1, then what can you say? If K prime is less than this number, what can you say? There is no solution. Or what is n here? Let us call it n prime, this is right. So if the K prime, which is the current parameter, is less than this number, then we can clearly say that there is no feedback vertex set of size at most K. Otherwise, so in this case what we say, return no, okay. Okay, then we return no. Otherwise, what is the situation? K prime is greater than equal to n prime 2 delta minus 1, right, which implies n prime is less than equal to 2 times k prime delta minus 1. Agree? Okay. So, number of vertices has become, look, I am only looking to bound by k delta. So, this is already order k delta, right, but we have still not bounded the number of edges in the graph. But how many edges in the graph can be? Let us see. I have f and I have here. So, how many edges are here? K prime delta at most plus n minus k here. Forget minus 1, I don't care. But what is n? Is again bounded by some k delta or k prime delta. It's same k prime, k is more than k prime, so this is fine. So, this is what? Order k delta. It's just substitute n equal to this, doesn't matter. It means what we have done, we have shown that the number of Vg prime, size of Eg prime is bounded by order k delta. So, nothing, you apply these simple reduction rules, right? If you apply these simple reduction rules, if the number of vertices is more than, say, you return no, otherwise whatever the graph you have, you just return that and that's it, you are done, right, and that has a desired size bound. Okay. So, this is what we will do. Now, what is our, okay, so we are done with the step 1 and step 2. Okay. Now, the whole goal I am going to show to you how will we do that. The delta will become, if I show that the maximum, if I apply some reduction rule and show that the delta of the graph delta g is some order k, aren't we done then? If I show that the delta g of the graph, maximum degree of the graph is bounded by order k, then I have got my order k square vertex kernel for order k square kernel for feedback vertex set, because I substitute delta equal to k and I can do this maths. So, the whole in the remaining part is all about getting down the degree of the graph. Okay, all well? Okay. Okay. So, this gives us kernel of size order k delta. Okay, fine. I am going to rub everything except this part and we will get there. Okay, I can probably start from here. Okay. So, the whole purpose or whole goal is, okay, do you remember a high degree rule in vertex cover? What was the high degree rule in vertex cover? What was the high degree rule for vertex cover? So, the rule was and there exists vertex V this one, then V is part of every solution of size at most k. because if you do not take him, you have to take k plus. What will be the canonical rule for feedback vertex set? What will be a rule analogous to this for a feedback vertex set? More than k cycles? Exactly. Okay. So I'm going to define a notion of X flower. Okay. What is an X flower? It's basically there's an X and there are hanging vertex adjoint cycles. So what is X flower? Basically X with several cycles passing through X, say C1, C2, Cl, such that except X they are pairwise vertex disjoint. Okay, this is exactly how it looks like. So this is, think of this as a cycle. Right, except that there are only one vertex in common, X. Now if you have a k plus 1 such vertex adjoint cycles, like if you have a vertex X with such k plus 1 vertex adjoint cycle and you decide not to pick, then any feedback vertex set must pick one vertex each, and since they are vertex adjoint, it's very natural, right? You will at least pick k plus 1 and that's not good. So if I am able to detect a X with k plus 1 vertex adjoint cycles hanging through it, then I have a proper reduction rule, pick X and decrease k by 1, right? So the order of X flower, I will X flower of size k plus 1 means there are k plus 1 cycles hanging from here, okay? So what is the reduction rule? Okay, so the reduction rule is, I have not even told you how to find X flower. But if I am able to detect X flower, I know I have a reduction rule. Okay, so here is the reduction rule, and this is a very crucial reduction rule. Let Gk be an instance of FVS, feedback vertex set. If G has an X flower of order k plus 1, of order at least k plus 1, okay, then remove X and decrease k by 1. So basically G comma k and this reduction rule is obvious and I am not going to prove it correctness. Okay. Okay. So what I want to do is that I am going to state a lemma which prove, either I can give you now or I can postpone and first to the kernel, either way I am fine with it. And then, so we are quite differing quite a lot from the paper or something. So okay, so what I am going to prove a nice lemma. So here's my lemma. Let G be a multigraph. Okay, what is this? Let G be a multigraph and X be a vertex of G without a loop. Okay, then in polynomial time we can either decide G comma k is a no instance of FVS check whether there is an X flower of order k plus 1, or find a feedback vertex at Z subset of Vg minus X of size 3k, of size at most 3k. So let's parse this line. So what he says, I'll give a polynomial time algorithm. So you give me a vertex X, and the only thing which I'm demanding that it does not contain a self loop, which is fine, because if it contains self loop, our previous reduction rule would have applied. So then I say in polynomial term, some way I will tell you that no, it's a no instance, or I will find you a X flower, or I will find you a feedback vertex set of graph of this graph which does not contain X of size at most 3k. Right? So I do three things to you. Either I will tell you it's a no instance, then you return no instance, or I will give you a flower of order k plus 1, in which case you can apply flower rule, this reduction rule you can apply, and you can restart all over again. Or I will not do this, I will give you a feedback vertex set of size at most 3k, which does not contain X. The important point is it does not contain X, right? It does not contain X and has size at most 3k. Okay. So so if you look at the paper or this or the book, the proof relies on what is called Galai something. I don't know. I do not remember, some very heavyweight theorem. Okay, but there is another alternate combinatorial way of doing this, and this is an alternate combinatorial way of doing this. Either I can give a proof for that, I mean, which will do, or let's apply this and let's get a kernel and then come back and prove this lemma. So up to you people, whatever you want. I am fine with either way. You want to prove this? Okay, let's prove this. Okay. Okay. So let's prove this. Okay. So I start with, so I'm going to assume a fact 1, that feedback vertex set has a factor 2 approximation. Okay. That is the only assumption which I'm going to do. If required, if we do not care, I mean, there are many ways of getting an approximation algorithm. For example, if you do not care about the sizes, then if you have seen a degree branching rule, you do degree 1, degree 2 reduction rule, and whichever vertex goes into solution, take it. Take the first 3k vertex, you know there is at least one vertex which goes into solution, delete all of them. So if you repeat this more than k steps, you say no, or you have found an order k square vertices whose deletion gives me a feedback vertex set. So that's a simple feedback vertex set approximation, but that's not order k that will not give you some constant factor, but order k approximation, which is good. It might just add a k cube kernel for feedback vertex set, but for illustrative purposes, that's a kernel. That's an approximation algorithm which we could use, for example. But so for now, let's assume that we have a good factor 2 approximation, because that's not what is the key point of the lemma is. Okay. So first, what I do, apply factor 2 approximation, apply factor 2 approximation on G, factor 2 approximation for FVS on G, and obtain a set or obtain an FVS S of size less than or equal to 2 times opt, because it's an approximation algorithm. It is not going to care about k or something, it gives me this. Now what I do, I check if S is more than 2k, what is an answer? Because if my approximation has factor 2, it means my solution, my feedback vertex set size should at least be half of whatever I output. So half is strictly more than k, and hence it's a no instance, and that is why you are returning a no instance. So that we return. In this case, return no instance. Agreed? So what is the property now? So now from now onward, S is less than 2k. Okay? Okay, so here is my x, here is my S, and now I have been given x. Okay? I have to either check this or check to, or either do this or do that. Suppose x is outside S. What can I do? If x is outside this set S, then the Z, I can return S. Actually, it says size at most 2k, right? So in this case, I have returned a feedback vertex set of size, in fact, at most 2k, which does not contain x. So we are great. So the bad part is x belongs here. Okay, agreed? Now let's see how do we deal with this. Okay. Okay, fine. And this is an interesting case. Okay, what is this? That x is a part of S. X is part of S. Fine. Okay, but I'm going to partially construct Z. I'm not going to leave Z, but I'm going to partially construct Z. Z is going to be S minus V plus something more is coming. So I add all but x. So I do not, I said hey. But now notice, what is your graph left with? All the cycles in, after I deleted S minus x, here is your forest and here is an x. All the cycles that is left are passing through x. There is no more cycle which does not pass through x, because Z or because S was a feedback vertex set and we have removed all vertices except x from the graph. So this is a forest where all the cycles, if I put back x, all the cycles, if at all it forms, it must be passing through x. So all it boils down to taking care of all the cycles that pass through x. Right? Is the goal clear? Okay, so let's do that. So we do it slightly differently. Okay? Okay. So this is what I call, let's zoom in more. Okay? So here is my x, and here is my forest. This is what? G minus S. There could be lots, it's a forest, so there could be lots of small trees. I'm going to concentrate on each tree, okay, separately. So let's call this tree T1, T2, TL. There are L trees. What is my objective and what is my plan? My plan is to find, okay, let's, and then we will see how do we implement the plan. The plan is, what I want to do, that I look at the neighborhood of x, neighbors of x in these TIs. My goal is either I somehow pair these neighbors by vertex adjoint paths, somehow I pair them by vertex adjoint path, these neighbors, because if I pair them, suppose for example this is one vertex adjoint path, 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 then what is it giving us? If you notice, this guy is adjacent to this, right? And these are the only thing, and none of the other vertices will be from this. So only the endpoints will be the neighbors of x. Then what is it giving us? Actually it is giving us a cycle, right, passing through x. This is giving us a cycle passing through x. This is giving us a cycle passing through x. This is giving us a cycle passing through x. So if I can do this several times, k plus 1 times, then I am able to get k plus 1 flower. Okay. If I will not be able to succeed, then I will tell you that I will find a set W, so that if you delete this W from the graph, every connected component here, like in fact, if you look at G minus S minus W, it will have the property that look at any connected component here, it contains at most one neighbor of x. What will be the property? Here, every connected component contains at most one neighbor of x. And then I am saying, then you have no cycle. Why? Because how can you have a cycle then? Think about it. After I delete W, then I'm claiming to you that this graph has no cycles. Because every component is what? Has exactly one neighbor of this guy. So now I go, look, I go for the cycle, and well, with one vertex I have only one neighbor, right? Until unless I could have had this multiple edges and these things, I mean that could happen. That what happens if this happens, right? Multiple. We will take care of that. Okay. Then that's a cycle in itself. Probably we would have handled it separately. Okay. So such objects do not exist. Every guy is like this graph becomes a very simple graph. Okay, it's a simple graph because there is, of course, there cannot be a parallel edges here because those are cycles. So this part of the graph is simple. And remember, after I delete x, so we will make sure that you do not have this kind of parallel edges. Then what does it mean? If I come into this component, I need to go out also, right? But go out to where? I have to go out to x, but then some other neighbor will become a neighbor of x, and that's not true. So if I am able to find W, which basically cuts all the path here, cuts all the paths here, we are very good. So that's a plan we are going to execute to implement this lemma. What is the goal? We'll try to build these paths somehow. If we are able to succeeding in finding k plus 1 vertex disjoint paths, great. Or we find a set W with the property that none of after I delete this, every connected component will contain at most one neighbor of x, and that will be the plan. And since W size will be k, if I add W here, the Z will have size at most 3k, and it is a feedback vertex set of the whole graph. Okay, so that's a plan we are going to execute. So how are we going to execute this plan? Okay, is the idea clear? Idea, at least proof plan is clear. Okay, so what we are going to do, we are smart people. So I'm going to concentrate a process on one tree. Okay, and we will repeat this process to every tree. Okay, one tree Ti. Okay, and what we do, we root this tree I at some Ri, just root it at some guy, it does not matter, some. So you fix a tree Ti and you root it at Ri. Okay, I can send you my notes, it's fine, it's okay. I mean you don't have to like kill yourself like trying to take down everything. Okay, okay, but what is my goal? So first thing let's do is let's mark some neighbors of these guys. These are the neighbors of my x, and I'm going to call them n of ix is nothing but okay, this is what it is. Okay, I don't know what is it. Okay, okay. Now I'm going to make H. Okay, there are some clever tricks here. Okay, H is basically u comma v, it's a pairs u comma v. U comma v is in ni of x. Okay, so for example we could have applied certain kind of reduction rules here itself. But I will, okay, so this is what it is. Okay. Now this is H, it basically denote the set of pairs formed by the vertices in NIX. So basically these are pairs formed by the vertices in NIX. This is what it is. Okay. Now what I want to do, for every UV I want to associate their common ancestor, least common ancestor. Now what is the least common ancestor of these two guys? Huh? No, this itself, exactly. If they are on the same path, the least common ancestor of pair of vertices is itself. But the least common ancestor of this guy will be this. Least common ancestor of this guy is Ri. Least common ancestor of this guy is this. Least common ancestor of these two guys is this. Least common ancestor of these two guys is this. Least common ancestor of these two guys is this. Right? So this is what I mean by least common ancestor. Okay. So what I'm going to do, I'm going to associate with every pair UB its least common ancestor, which it could be itself. Right? Which it could be itself. Okay, so for example, so there's a question about self loops, right, or parallel edges between two vertices, right? So if there are such vertices, how many of them are there? At most k of them are there. Otherwise, if there are k plus 1, you already have got a flower. So you could have did. So just think that they do not exist for now. Okay. Otherwise, we can just delete those k vertices, put them separately, so that there are no more parallel edges, all are singleton edges, and we can deal with it separately. But I don't think we need to. Okay. Okay. So for every pair of vertices, UV, let AUB be the least common ancestor of U comma V. Right? And as I told you, AUV could either be U or V, and that will be if they are on the same path. Okay, fine. So now what I am going to do, now here comes the fun. Let L be the list of common ancestor. It could be multi-list. How? Look at this pair. Look at this pair. Which is your common ancestor? This guy. Look at this. Which is this? This is the least common ancestor. Okay. So L is a list of common ancestor where multiplicity is allowed. Right? A vertex can repeat. Okay. It just says that for this pair this is your least common ancestor. For this pair this is your least common ancestor, and it can happen all over the place. Right? So for example, here if I had another vertex here, then for these two guys this is the least common ancestor. These two guys this is the least common ancestor. These two guys this is the least common. It could be anything. Okay. So now we want to associate a depth to least common ancestors. What is the depth to a least common ancestor? And this is why we have rooted the tree. Okay. So the depth of a guy is how far it is from the root. That's it. It's very simple definition. Okay. So now what we do, now we sort the list L based on list L, okay, list L by decreasing order of their depth, by decreasing order of their depth. So the guy which is the most, which is the like furthest from the root will come before, and the guys which are closer to the root will come later out. Right? So this is what we mean. Now we have sorted it out. Okay. And now here's my simple procedure which does the job. Okay, so what is my simple procedure? Okay, let's see if you understand this. While the list L is non-empty, we do as follows. Okay, while the list L is not empty, let's do as follows. Let UV denote the pair. So what is an idea? If you just to let you know what I'm trying to achieve at this point of time. I'm trying to, whatever idea I told you, I'm trying to organize this in a methodological manner, right? So what I want to do, I said, hey, this is there's a pair for which this is the least common. Let's pick this path and put it separately, and then whichever damage has happened, let's subtract it from this, and just keep doing this while the list is not empty in this organized manner. And that's all that I want to do, and I want to prove that this is correct and optimal, right? So all I have to do that every time whenever I will do, first of all, the paths which I will put into my list, they will be pairwise vertex adjoint, right? So if this grows to at any point of time k plus 1, I said okay, do. And for every path I will add a vertex which will destroy all paths below and him by one vertex. So it's basically min-max theorem, right? Minimum number of vertices to destroy all the paths between them is exactly same as maximum number of vertex adjoint paths between the pairs, and this is exactly what I'm proving to you. What I'm proving is a min-max theorem at this point of time, that look at a forest, look at all this neighbor, maximum number of vertex adjoint paths on this colored vertices is same as the minimum number of vertices needed to break all these paths, and that's all that I'm doing. Okay, so if I would have told that way, it would have looked a bit more weird, but this is what actually I'm trying to prove in my head. Okay, and the question is, why would suddenly someone think of this way? Because it's a forest, so they have something called Helly properties and all this, so that gives you an idea that this kind of theorem could be correct. Okay, so I'm just trying to organize my thoughts in this order. Let UV denote a pair for which AUV is the first vertex in the list, right? Okay, is the first vertex in the list. Observe that the unique path PUV between U and V do not contain any other neighbor of NIX. A unique path PUV between U and V does not contain any neighbor of any vertex from NIX except U and V. You may say why? Okay, let's look at this path. So there are two cases. One of them, U and V, is an ancestor, or AUV is something separate. So for now, let's assume that they are separate. So they are separate means what? They are not on the same path. So here's the U, here's U, there's AUV. Okay. Suppose there is some other vertex from your neighborhood on this path. This is what we are arguing, right? So that guy is here or here. It doesn't matter, right? If it is here, then what about this pair? Larger depth, right? So I would have taken this, right? And same argument here, right? So this is okay. So at least in this case, it cannot be. And this case is even more trivial. If you have UV and there is someone else, then just take this pair, no? right? And so that's a property. That's a beautiful property, right? Okay. So this is where the least common ancestor trick and going to the depth has helped us. Okay, simple property, but interesting property. Okay, now what we do? Now we are doing great. Add AUV to X. This is where I'm the hitting set which I'm creating. So I add AUV to X. Okay. Add PUV to curly path. So this is a family of vertex joint paths which I'm trying to create. So this is my curly P. So I add this path PUV to this list. Okay, I will maintain as an invariant that this is vertex joint paths which I add. Okay, and now I do some destruction. Delete all pairs from H. Delete all pairs from H containing what? U or V, because they have been already used. So you delete all those pairs because they are because I want to maintain certain invariant, right? And what else should you delete? And delete all vertices AUV from L for which there is no more path in Ti minus X. Right? This is my destructive set. So I delete it. Now some guy is in the list because some U and V had a path, like, right? But if there is no path in Ti minus X between this U and V, then what is the point of that common ancestor? This, like, it doesn't make sense. This guy is no more a common ancestor. So it loses its position of common ancestor in Ti minus X, so just delete it. So you have cleaned up. So what you do, you among the list, you find your UV, which is the least guy, which is the property that there is no one else, add AUV to X, add PUV to P, and now we are doing some cleaning process. So this is like a cleaning step. What is the cleaning step? Delete all pairs from H containing U and V, which makes complete sense because you already have used U and V, and I want vertex joint paths, and delete all vertices AUV from L for which there is no more path in Ti minus X. Meaning, there is no pair for which this is a common ancestor anymore. What's the point of having this? So just delete those guys. So you have cleaned up your list. Okay. Okay. Now let's make an interesting observation. Observe that in H, which is current H, there is no pair of vertices A and B U and B such that either U or V belong to the subtree rooted at AUV in Ti. Okay. So now let's look at some subtree rooted at this guy. Suppose this, and I'm claiming there is no pair UV such that any U or V belongs here. Why? What will happen?
If we consider that pair of vertices, it will have a larger depth.
Exactly. So if I had a pair UV here, some U and V here, right? Some U and V here,
have a W here.
What?
We had U and V we had initially, and
Yeah.
we have a W here.
Yes.
And so we are saying
We
that
should say, yeah, there is no pair, say, ZW such that either Z or W belong to the subtree rooted at AUB in T. Okay, this is correct. You're right. Because if you had some W and Z below this of this nature, then why did this not happen? Okay. And but what about this? Why can't this way happen?
because their common resistor would be AUV.
Yes. And what we decided to do? Delete. Right? So when you put this X, right? When I decided to delete this X, this path does not exist at all. Right? So we have destroyed this path. So they cannot exist. Now, similarly, this someone here and someone outside cannot exist. Because again, if you are going somewhere outside, then you have to pass through this common ancestor, right? Or you have to pass through this route, but that vertex doesn't exist. So we have deleted those pairs from this. It means at this point of time, we have cleaned up certain set of neighbors. It means we can very well just take this guy and delete it, right? Okay. Delete the subtree rooted at AUV. And that's it, we are done. What we have done, what we have achieved is that every time we add object to P, right? Every time I have given you a constructive proof, right? Every time I add a path to P, it is vertex edge joint. Who makes sure of this? This step makes yours, right? And this step makes yours because this path was in the tree, subtree rooted at AUB. This path was not going anywhere else. This path was at the subtree rooted at AUV, and I deleted that. So every time I do this operation, I make sure that the subtree rooted at this below, this guy is deleted. It means every time I find another path, this is going to be a vertex edge joint because I'm completely scratching the subtree itself here, right? So that makes sure the paths which I add to P are vertex edge joint. Okay. And what does this step? What happens if this step is repeated k plus 1 times? If I repeat this step k plus 1 times, then I have added k plus 1 vertex joint paths in P between the neighbors, right? Okay. Then I have got a k plus 1 flower. No, so this process did not repeat. But then what is the property of X, which I have done? What is this guy doing? You are from H, you say, hey, which all pairs of vertices cannot have path after I delete X by removing it, right? So why are you not able to repeat this process? Because there is no more pair left. So X destroyed all the pairs. So X hit all the path. So at the same time, if you notice, I was adding one guy here and adding one guy here. So I proved to you a completely min-max theorem, right? So if you just repeat this process till it finishes, exact amount of thing you have added here and exact amount of thing you have added here. So what you have shown, and the exact amount of thing which you have added are vertex joint paths, and exact amount of thing which you have added. So after you destruct them, there is no more path. None path exists, right? So I have given you a constructive proof, and this is like simple polylinear time algorithm, right? If I gave you a graph and a vertex X, this is constructive. I look at this common ancestor and I can repeat this process. Is there any process, any step of this algorithm which looks exponential in this algorithm which I described to you? Right? So what I have given you, right? So I run this process on all HTI. If I get a flower, I apply flower rule. If I don't, then I have found a feedback vertex set for you of size at most 3k, which does not contain this vertex, and that's it. Okay? Is the proof clear? Okay. Okay, fine. So now, this is a key lemma. This is a key structural lemma. Okay. So I pick a vertex because what is my whole objective is to decrease its degree. Okay? I have 13 minutes left, so I cannot give you a complete proof at this point of time, but let me give you how we apply the reduction rule. Okay? Sketch, and then we will do the real proof. But after this, there's absolutely nothing. It's like really beautiful imagination. Okay? Okay. So let me rub everything else. Okay. So what I'm going to say, my whole objective is to decrease the degree of x. We didn't find the flower, otherwise we would have applied deleted x, decrease the k minus 1. So we have found some 3k size feedback vertex set such that it does not contain x. Okay, great. So now the picture looks like, the world looks like as follows. Here is my S. What I was calling it? Z. So let's call it Z, and I'm going to call it X because this is created for X. Okay, let's delete X, and let's delete X. So I deleted ZX first, then everything is forest. Now I also delete X, so I get connected components here. Connected components here. Okay. Question number 1 to you: how many neighbors can X have in any component? At most 1. Suppose X had 2 neighbors, had a cycle, then why did you say that X is a feedback vertex set? No. So that's point 1. Maybe some guys may not even have a neighbor to X, that's okay. But every component has exactly one neighbor to X, and that's important. Okay? Okay, so observation, let's write down. Okay? CL. Okay. What is an observation? Is that neighborhood, okay, n of x intersection Ci is upper bounded by 1. Okay. Okay. If the number of neighbors to which x has a neighbor was already small, then we are happy. Hey, we are done. Because then how many neighbors it can have? In each of them, it has exactly one neighbor, and to these guys, it can have certain amount of neighbors. But we have to remember that we are allowing multiple edges. But in a moment, we'll say that between any pair of vertices, you don't need more than 2 edges. If there are more than 2 edges, like third, delete it. It does not affect. So either between any pair of vertex, either there is no edge, or there is one edge, or there are 2 edges. So that will be, so the total degree at most will be 2 times zx, because we don't know how it is, and as many as components here it is. So it's, what is it making it too many neighbors is, there are too many neighbors to which this guy has a neighbor, because this is already controlled fashion, because this is like 6k here. So this is not to worry about. Only thing to worry about is how there are too many components, and to take care of those too many components, we apply a beautiful trick. Okay. We say, okay, fine. We compute an auxiliary bipartite graph, Zx, okay. Here, all those components, say everyone has neighbors for now. So all these guys are a vertex for each component, okay. And I put an edge between this guy and this guy. If there is a vertex here and here, if there's an edge between that and that, then I put an edge between this component. If even there exists one vertex here, such that it has a neighbor to one of these guys, then this component and this vertex has a neighbor, right? So this is how, basically think that I have shrunk each of the connected component into singletons. And I forget the edges here, inside edges, I forget. So now this is a bipartite graph. Question number 1, is it possible that there exists a connected component which does not have a neighbor here? Is it possible? Is it possible that there can be a connected component who has absolutely no neighbor here? No, because it's a tree, it's a forest, so it's a tree. So there's a degree 1 vertex. Graph at minimum degree 3. So this guy must be having a neighbor here, because in this worst case it can have one neighbor here. So everybody here at least has one neighbor here, for sure. The guy may not have a neighbor to him, this I can agree to you, but everybody has a neighbor here. So and I'm only interested in reducing its degree, so I should not be actually caring about those connected components which are not connected to X, right? But for now, let's assume that everybody has a neighbor to X. Everybody has a neighbor to X. Now, I'm going to say, hey, look, look at this size, let's call it B. If the cardinality of B is greater than or equal to 2 times ZX, then what does expansion lemma tells us? There exists a set here, and there exist components here such that everybody here, I can make them collection. And what is another property? Another property is all their edges are here. They do not have edges here. So all their edges are here, 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 here. Okay. But now let's look at something very beautiful. Okay. This is what I have locally, I'm going to apply min-max theorem. But what was this component? They all had X here. Okay. So what is the property? Basically we are getting a flower of small size. Right? This is what you are getting if you notice. There is a cycle passing through which passes through X. Now I'm going to claim to you what we can claim. Every optimum solution either contains X or let's call this X here or X. Every solution, okay. If it contains X, well and good, absolutely no issue. But if it does not contain X, then what happens? You must be picking up some vertex here or here, 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 right? What you do, look at all these guys, delete it and put everything in the X. And you will be able to show that is also a feedback vertex set. Why? Because from each of this cycle, now that you are not decided not to pick X, you are going to incur as many vertices as the size of X is. Right? So what you do, you forget the vertices here and you push it to X here. Because after you delete these guys, hey, these guys have no neighbor anymore. They are like degree 0, degree 1 vertex. So my degree 0, 1 reduction rule will take care of them and then just get rid of them. Right? So you prove this combinatorial lemma. And once you prove this combinatorial lemma, how do I remember the fact that X or these guys? So what I do, I will delete all these edges and X and these guys, I'll make a double parallel edges if it does not exist before. And I will delete all these edges. And that's the reduction rule. The reduction rule is delete all these edges and add this parallel edge. But now you might be saying, oh, what is the progress you are making? You're deleting some edges, adding some edges. So you have to show that you will not be doing this process more times, and for that what you do, you associate a very beautiful measure. So the measure which I like to associate is that for every vertex, number of neighbors with exactly degree 1. So how many, what is the measure of a vertex is? A vertex is, so summation of this thing. So mu, which we will associate, is summation of mu of V in Vg. And what is mu of V? Number of vertices with exactly one edge. Right? And I am claiming to you this definitely decreases, because these guys you are adding double edges, right? But from here you are at least deleting one edge, right? So the number of vertices with exactly degree 1, like exactly one edge to you, is decreasing. So you can show that this measure decreases all the time. So this process cannot happen eventually. So if this process cannot happen eventually, it means the number of components would have been bounded, hence the degree would have been bounded, and hence we could have applied everything else before, right? So it's all about formalizing this argument, right? So the reduction rule is very simple, but it's all about showing this combinatorial property, and which is not very hard if you understand, right? Oh, if it contains x, then because you have to show that after you delete this and I have added this, these two are equivalent instants. But that's very simple. If it's like if x went into the solution, then anyway these edges do not exist. You deleted it, so all is well. The old graph and the new graph is same. If it contained all this guy, then still all is well, because once you have deleted this, all this becomes a forest or degree 1. You will apply degree 0 or degree 1 reduction rule, all this component will vanish because they do not have any more edges. In the backward direction, either this or this now has to be part of the solution because you have added double cycle. So if you pick this, automatically you will prove the things there, otherwise this. So like the proof is very verbatim, very simple, but what is hard is like you have to like grill through yourself, prove this bound. Look, we have crucially used the fact that we have hit all the cycles passing through x without using the vertex x, right? In fact, we have proved even more thing. We have actually found a feedback vertex set without x, and this is true about any vertex. So either the guy gets a part of cycle and gets killed, or we are able to find a feedback vertex set without containing him. Okay, it requires at least half an hour of more rigorous proof to prove these things. So I will leave there, and when is the next class? Next Monday I'll finish this argument. Okay. Okay, thanks.